In section 2, first we defined center of mass and center of gravity. Center of mass, we know it. It is the point where we consider the mass of all objects concentrated and accumulated. Center of mass. And we can find center of mass by two ways. One of them is supported. Center of mass. Or throw it up air, because I will not throw it, this is $10. I can throw something else. Hammer. Okay. Did you see that movie that I sent you about the hammer? It was really nice. It was rotating about this point so slow and you saw it. So when we throw this up into the air, it will start spinning about center of mass in here. You can support it or you can throw it up into the air about center of mass. It will start to spin. And when you throw the hammer up into the air, hammer exhibits two motions. One of them is translational motion. You throw up into the air, it moves. Central mass is moving. Central mass moves with parabolic pattern. Just like you throw a rock up into the air. So the central mass follows the same pattern. But ends of the hammer will be following circles about the center. So I said that these two are important. You can really miss your question. Central mass follows parabolic paths of the projectile, but at the same time, ends of the hammer trace out circles. And generally, midpoint is the central mass for regular shaped object, but if this object is irregular shaped, what are we going to do? Central mass is going to be closer to heavier side. Center of gravity is same as the central mass, but only definitions are different. Central mass can be defined everywhere, but center of gravity only defined in Earth where there is a gravity. So that's why it's defined as the center position at which we draw gravitational force. And from which point we are going to draw Fg. That point is center of gravity. And equilibrium problems in chapter 2. There are two equilibriums, you remember. One of them was translational equilibrium, the other one was rotational equilibrium. In translational equilibrium, we are looking for net force to be zero. If net force acting on object is zero, the object is said to be in translation equilibrium. This is how we represent it. In some problems, forces are going to be inclined. That's why sometimes we need to resolve them into components. So some of the force acting along the x-axis must be equal to zero. Some of the force acting along the y-axis must be equal to zero if we are talking about translation equilibrium. But rotational equilibrium is similar to this one. In fact, you can predict it. Rotational analog force is what? Torque. That's why it must be about torque. Sum of the torque acting on the object must be equal to zero. In this case, we say that rotational equilibrium exists. But if both exist, translational equilibrium and rotational equilibrium, we say that the object is in complete equilibrium. These are the conditions. For translation equilibrium, net force must be equal to zero on the object. For rotational equilibrium, net torque on the object must be equal to zero. But measuring net force to be zero or net torque to be zero is not very easy always, because you don't see the torque, you don't see the force, but we see what? Motion. If net force zero, which means linear acceleration is going to be zero. Linear acceleration zero means object will be at rest or object will be moving with constant velocity. Constant velocity. What does constant velocity mean? Object must be moving in a straight line path with constant speed. If rotation equilibrium exists, net torque should be zero. As I said, net torque is not very easy to know if zero or not, but we can check what? Alpha zero. How alpha becomes zero? Object is going to be at rest or object will be rotating with constant angular speed. Yani you can go from this to that. If angular speed of a rotating object is constant, there is rotational equilibrium. If linear velocity is constant, there is translational equilibrium. If object is at rest, there is translation at rest, rotational equilibrium. Everybody knows, I think, remember that for a rolling object, linear and rotational quantities are related by an equation. V is equal to R times omega, just like how tangential speed related to angular speed. Or linear acceleration and angular acceleration are related. A is equal to R times alpha, just like how tangential acceleration and angular acceleration are related in circular motion. So everybody knows about that. I will skip this. Good, we did it in the solution of the problems. First one, a bicycle wheel. So this question is talking about what? Wheel itself. Sometimes you are just thinking about the points on the wheel. No, it's not saying that. Point on the wheel. No, it's about just the bicycle wheel. A bicycle wheel rolling along a level highway. Level means not incline, it's flat. Highway, but rolling at constant speed. Constant speed, oh, which one's constant? Translational or rotational? Both. Because you know they are related. So if one of them is constant, the other one should be for another object. Did we say that they are related by an equation? Remember that? V is equal to R times alpha, which is omega. If this is constant, that is constant. Yani, for a roller object, if you say omega is constant, V is constant. Both are constant. V constant, omega constant. If speeds or velocities are constant, accelerations are zero. Zero linear acceleration, zero angular acceleration. Yani, linear acceleration is a no. Translation equilibrium is a yes. They are always opposite. Angular acceleration is a no. Rotational equilibrium is a yes. Next, bicycle will parked. Parked, what does it mean? Velocities are zero. They are at rest. Then no linear accelerations. Linear acceleration is zero, no. Rotational equilibrium, yes. Angular acceleration is a no. Rotational equilibrium, yes. Tires. But this question is talking about what? Tires. Just a tire, not the car. Tire. Tires on a brake automobile. Yes, yeah. The question is automobile, but question is not about automobile being equilibrium or not. It's about tires. Tires on a braking automobile, there is still mobile. Braking, what does braking mean?
Slowing down.
Yes. Slowing down. Both are decreasing. Angular speed is decreasing, linear speed is decreasing. So in this case, accelerations cannot be zero. If accelerations are yes, equilibriums are no. What did I say? If for a rolling object both are yes, yes, or no, no. In rolling object we don't have yes, no conditions. So both equilibrium holds or none of them holds. And the last example was this. A football traveling through air. So when we throw a football up into the air, which equilibrium holds, which one not? First, there is a net force. Net force is a yes. So translation equilibrium is a no. Free fall acceleration. Acceleration, linear acceleration is a yes. Translation equilibrium is no. What about rotational equilibrium? Check the torque. Gravitational force x squared. Center. Eccentric x torque rotation. If a force acts x rotation, what's torque?
Zero.
Net torque, zero. If net torque is a no, rotational equilibrium is a yes. Yes. And equilibrium problems. Let's solve one problem like this. Equilibrium. This is the popular one, most popular one. A 700 Newton window washer is standing on a uniform scaffold supported by vertical rod at each end. The scaffold weighs 200 Newton and 3 meter long. What is the force in each rope when window washer stands 1 meter from one end? Okay, let's draw a window washer. What is scaffold? Scaffold is a board. What is the length of the board? It is 3 meter long, and there are 2 ropes at each end. Let's draw them. One rope is on the left end, the other one is on the right end. So they are, of course, attached to somewhere. But this scaffold has some weight. 200 Newton. Uniform. Why I carry it? Because for uniform, center of gravity is midpoint. So I will draw gravitational force from midpoint. How much? 200. Ft for scaffold is 200 Newton. So if it is midpoint, it divides the scaffold into 2 equal parts. 1.5 meter on the left, 1.5 meter on the right. What is the force in each rope when the window washer stands 1 meter from one end? So I'm going to locate the window washer 1 meter from one end, because I put it here, right? But let's put this time right side, okay? When you will be moving the washer somewhere in here. Okay, 1 meter from one end. The distance is going to be 1 meter from right end this time. Find the force in each cable, because each rope exerts a force. Ft1, I will say this one. Ft2, I will say that one. Of course, the man will be pushing the rope, this scaffold down. How much is the force of the man? Fg? It is what? 700 Newton. Find Ft1 and Ft2. Which one you are going to start? It's up to you, because I'm a right-handed person. I always start from right. There's no specific reason for this. So I will first calculate Ft1. If I want to calculate Ft1, I have to choose location of other unknown force as axis of rotation. Axis. Then, distances. Check the distances. Distance for Fg, well, let me label them Fg1 and Fg2. For Fg1, what is distance? 1.5. For Fg2, I need it. I can find it. Total length is 3. That side is this must be 2 meter. Yeah, 3 minus 1 is 2. I got it. What about distance for Ft1? 3. So distances are ready. Then calculate torque of each force. What is torque of tension 2? 0, because acting on x rotation. Torque of T1, these are all lever arms, perpendicular distances. This produces a clockwise rotation. Its torque is going to be negative 200 times. How much is the distance? 1.5. It's going to be 300, I think. Negative 300 Newton meters. What about Fg2? It produces also negative torque. Torque of G2. Torque of G2. It's negative. How much is it? 700 times 2, which is going to be negative 1,400 Newton meter, correct? And tension 1 produces a positive torque counterclockwise rotation. Torque of tension 1 is going to be a positive Ft1 times, what is distance for it? Lever arm 2. There are 4 forces acting on the scaffold. I found 4 torques. Now apply rotational equilibrium. Sum of the torque acting on the board must be equal to 0. So add them. Torque of tension is 0. Torque of Fg1 negative 300. Torque of Fg2 negative 1,400. Torque of tension 1 plus 3 Ft1. Result is this is 1,700 negative. On the right, positive. 3 Ft1 is going to be positive 1,700. Divide them by 3. Ft1 is going to be how much? 567 Newton. After finding Ft1, FT2 is easy, but if one unknown force is left, we can find the other one by applying translational equilibrium. So all the forces are acting along y-axis, so I'm going to apply sum of the force acting along y-axis must be equal to 0. Start from FT2. Unknown, I will find it, write it. FT2. Then go with FT1. Negative 200. We are not writing this, we need this. What about FT2? Negative. What about FT1? Positive 567 is equal to 0. Then you are going to first calculate them, transfer it to the other side. FT2 is going to be, I think, 330. What do you mean? 333. Tamam, bu kadar yeter. This is how we solve equilibrium problems. Evet, vaktimiz oldu galiba. Section 3'ye geçemedik hiç. Sağlık olsun ne diyelim. Section 3'de videolardan bu akşam bakarsınız.